Hey, what's up my chemistry people? What in the heck are we gonna do in this video? We are once again gonna make some qualitative or quantitative predictions about redox reactions, reduction, oxidation, based on half-cell reactions and potentials. Let's break it down a little bit. First thing we're gonna do in this video is determine the value for standard cell potential for a given redox reaction. And then numero dos, we're gonna explain what the value for that standard cell potential means in terms of thermodynamic favorability. Is it spontaneous or is it not? All right, so when we talk cell potential, abbreviated using this letter E with this little subscript cell, it is essentially the measure of the potential difference between two half cells, oxidation half cell and your reduction half cell. And that potential difference is caused by the ability of electrons to flow from one half cell to the other. Now, as you look at a reduction potential chart, if I were to choose two substances on this list, there's a potential difference that exists between those two things. The potential for one of them to gain and one of them to lose electrons. Imagine that one of those things is standing at the top of a hill and the other is standing at the bottom. So if this is copper and this is silver, and copper is trying to chuck an electron to silver, it can do that with essentially no external input of energy. But if things were reversed, and silver were trying to give its electron to copper, it would have to put a lot of energy in to give that electron back. You can do it, silver. Yes, you can, silver. You can do it. At any rate, the cell potential is just one way we can tell how likely it is for a redox reaction to occur as written. It's also known as the electromotive force or cell potential difference. So what you want to take away from the cell potential is this reaction going to happen spontaneously or is it not? Now, cell potential is measured in volts, which allows us to give a certain value, a numerical value, to the cell potential. Cell potentials under standard conditions are called the standard cell potentials, and notice the little naught symbol to designate standard conditions. And when we're talking standard conditions, we're talking 25 degrees Celsius, 1 atmosphere for gases, and 1 molar concentrations for solutions. So, how do you determine the cell potential for an overall redox reaction? You simply add together the reduction potential and oxidation potential for the two half reactions. Boom. Now here's the big one. The more positive that cell potential of a reaction, the greater the driving force of electrons through the system, the more likely that reaction will proceed. In other words, it's more spontaneous, more thermodynamically favorable, the more positive that E cell is. So again, important here, a redox reaction will be spontaneous or thermodynamically favorable when there is a positive E cell value for the overall reaction. However, if you have an E cell value that is negative for the reaction, that means that as written, the reaction is non-spontaneous and will only occur when an outside force or source of energy is applied. So let's take a look at these two reduction potentials that were stolen from our larger reduction potential chart. We've got two options. Our first option, copper is going to be reduced and zinc will be oxidized. Notice I flipped the reduction half reaction. As I assign potentials to these half reactions, my reduction half reaction is going to come from the reduction potential provided. But because I've written my zinc half reaction as an oxidation half reaction, the oxidation potential is the same numerically but opposite in sign. So when I combine these two to determine the cell potential for the reaction overall, all I do is add these two together, and I get a value of positive 1.10 volts. Don't forget your units. Okay, but what if we had done it the other way around? What if we had said that copper was being oxidized? That would mean that its oxidation potential would be negative 0.34 volts, and that zinc was being reduced. We would keep its reduction potential as what's given to us as negative 0.76 volts. Now when we combine these two equations and sum our oxidation reduction potentials to get the overall potential for our cell, we get negative 1.10 volts. So notice that the two processes are opposite one another. Here's how I've written it originally. This is the reverse process. One of them is spontaneous or thermodynamically favorable because I have a positive cell potential, One of them is non-spontaneous because I have a negative cell potential. It would have to put a lot of energy in to give that electron back. You can do it, Silver. Yes, you can, Silver. You can do it. That is it. We are done. Have a fantastic day.